Hello everybody and welcome to a new video. We will continue discussing measures of dispersion, and the next measure of dispersion that we're going to discuss is the variance. The variance of a variable is the square of the standard deviation. A population variance is noted sigma square and the sample variation is S square. So basically, if you could find the population standard deviation and the sample standard deviation, you will be able to derive the population variance from there very easily by squaring the population standard deviation, and we're going to be able to find the sample variance by squaring the sample standard deviation. Here's an example to illustrate how to find the population variance. The following data represents the travel time in minutes to work for all 7 employees of startup web development company, and we want to compute the population and sample variance of this data. Remember that we just calculated the population standard deviation and it was 11.36. So to find the population variance, you're just going to square that amount and that will result in 129.05 minutes. And also we calculated the sample standard deviation previously and it was 15.82. And by squaring that amount, you will get 250.27, which is the sample variance. Next, we are going to discuss how to use the empirical rule to describe data that are bell-shaped. The empirical rule states that if its distribution is roughly bell-shaped, then approximately 68% of the data will lie within one standard deviation of the mean. The next thing the empirical rule states is that approximately 95% of the data will lie within 2 standard deviation of the mean. That is, approximately 95% of the data lie between mu minus 2 sigma and mu plus 2 sigma. And the last thing the empirical rule states is that approximately 99.7% of the data will lie within 3 standard deviations of the mean. That is, approximately 99.7% of the data lie between mu minus 3 sigma and mu plus sigma. Please note that we can use the empirical rule based on sample data with x bar replacing mu and s replacing sigma. This shape here illustrates the empirical rule, and this shape is extremely important. We will be referring to this shape very frequently later on in the semester when we study hypothesis testing. So what the empirical rule says is if our data is roughly bell-shaped, so this is bell-shaped data, the mean is going to be in the middle of my data, so that is the mean. And then it states that 86% of my data will be within 1 standard deviation from the mean. So if you add 1 standard deviation to the mean and subtract 1 standard deviation from the mean, that set of data will represent 68% of my data. And then it also states that if you subtract and add 2 standard deviations to the mean, so add 2 standard deviations to the mean and subtract 2 standard deviations from the mean, that will represent 95% of our data. So that amount, this part of our data is 95% of our data. And lastly, it states that if you subtract and add 3 standard deviations of the mean, then you will get 99.7% of our data. So that is 99.7% of our data. And that will leave us with only a little bit at the tail here of my data and a little bit of the tail at my data, which represents 0.15% on each side. So that's a very little amount of data that I have. Please remember this shape very well. We're going to refer to it very often. Now let's look at an example to illustrate the empirical rule. The following data represents the serum HDL cholesterol of the 54 female patients of a family doctor, and the raw data is stated below. We want to compute the population mean and standard deviation, draw a histogram to verify the data is bell-shaped, determine the percentage of all patients that have serum HDL within 3 standard deviations of the mean according to the empirical rule, determine the percentage of all patients that have serum HDL between 34 and 69.1% according to the empirical rule, determine the actual percentage of patients that have serum HDL between 34 and 69.1. So I transferred my data into the spreadsheet. And the first step is to find the population mean, since we're talking about all the patients. in that family practice. So the population mean is basically is equal to the average of the entire. And then to round that, I'm going to go to this and click on numbers. So that will be rounded into two decimal places. And the standard deviation, I'm going to use the standard deviation and the population standard deviation function. Select all of your data and click enter. And that will be rounded here. Okay, so that is the first thing that we're going to calculate. Next, we're going to create a histogram to verify that our data is bell-shaped. So the first thing to create the histogram, I'm going to find the minimum amount. I will show you why I will need the minimum amount and the maximum amount. So I'm going to try to build my classes, which is in this case, I'm going to use bins instead of classes. So the minimum is all equal to minimum. And the maximum. So I found my minimum and my maximum. I'm going to start building my bins right here. So I'm going to say, I'm going to start at 35. I will use a class width of 5 in this case. But since I'm using the data analysis function, I don't need to build classes. I will just put the bins individually. So that will be 40 next. Next, I'm going to install the data analysis function. The data analysis function is installed by going to File. It's an add-in. So go down to Options, and from Options, you will find Add-ins. Click on Add-ins. This will pop up for you. Make sure this is Excel add-ins and then click Go. What we will need is the first one. It was unchecked. Please check it. We want the analysis tool pack, and then click OK. This will add it to the data tab. So to find out whether you added it to the data tab or not, you're going to click on the data tab, and it should be right here in the corner. It says data analysis. If it's not there, go through the steps again, and it should appear for you. So how to create a histogram? We're not going to use the insert tab. We will use the data tab for this histograms. What we are going to do is to select all of our data first, and then go to the data analysis, click on it, and then go to the histogram where it says histogram, and then click enter. It is going to ask you about the input range. So you go ahead and choose the input range, which is our data set. And the bin range, which is we just created right here. So the bin range is going to be here. Select all of these numbers. And then we want an output range. Where do we want our data to appear in front of us? If you don't do that, it's going to open a new sheet. So to do that, I am going to select some cells right here. And finally, we want to show a chart output that will create the graph for us, and then click OK. And it should give you the histogram. As you notice, the histogram here is not quite as the histogram we learned. Those are bins, are not intervals, which is not a big deal. Select your bars to make it look nice. Something like that will show up for you. And here you will see gap width. We want the gap width to be 0. So turn that into 0. And as you can see, it showed you a nice shape, and the shape here, it appears to be bell-shaped. So that is our proof that our data is bell-shaped, and we can continue with the empirical rule. And that is the frequencies it was created for us. Okay, let's go back to the empirical rule. Next, we want to determine the percentage of all patients that have serum HDL within 3 standard deviations of the mean according to the empirical rule. So I'm going to create a table right here that tells me the mean plus X standard deviation. So that is the mean plus 1 standard deviation and the mean minus 1 standard deviation. When I go down, it's going to calculate the mean plus 2 standard deviations and the mean minus 2 standard deviations, and etc. So to calculate that, you're going to click on the mean and please lock that cell. We don't want it to go anywhere. And then plus X, which is this cell. We don't want to lock it because this moves down. And then times the standard deviation cell, which is this one, and lock it, press in F4, and then click enter. And then we're going to populate the rest of my tables. So I will have something like that. To calculate the next one, you're going to say equals the mean cell, and then lock it, press in F4, and then minus X. We don't lock that cell because it's moving down, and then times the standard deviation, lock that cell as well, and then click enter to populate the rest of the table. We're going to do that. I'm going to delete the last one. So those are the numbers that I will be using. I'm going to highlight all of these and go to numbers to round them to 2 decimal places. Next, I will go to this shape, and now I can put the mean and the mean minus 1 standard deviation and the mean plus 1 standard deviation, and I can refer back here. So my mean is 57.41. So that means the middle number is going to be 57.41. So this is 57.41, 7. And then plus 1 standard deviation is going to be that amount, so 69.10. This means this is 69.10.1. And then minus 1 standard deviation will be 45.7. So this is 45.7. And then plus 2 standard deviations will be 80.8. So this will be 80.8. And minus 2 standard deviation will be 34.02. So this is 34.02. That's a 3. And the last one is within 3 standard deviations. Plus 3 standard deviations is going to be 92.5. So this last one will be 92.5. And this last one will be 22.32. 22.2. Notice here that we can just skip that number altogether. We don't need it. It's very small. So to find the second one, which is determining the percentage of all patients that have HDL serum within 3 standard deviations of the mean according to the empirical rule, let's see within 3 standard deviations what it's going to look like. We will be adding 1 standard deviation, 2 standard deviation, 3 standard deviation, and stopping right here. And 1 standard deviation, 2 standard deviations, 3 standard deviations. We'll stop right here. Remember, within 3 standard deviations, our data is going to be 99.7%. So that is the answer to the third one, which is determine the percentage of all patients that have serum HDL within 3 standard deviations of the mean according to the empirical rule. And the fourth one is to determine the percentage of all patients that have serum between 34 and 69.1 according to the empirical rule. So this is where we're going to use the data that we just collected. So let's look here. So this is the 34, and that is the 61.9. And the question is asking to determine the percentage of all patients that have serum between those two numbers. So let's count the percentages between those two numbers. That means we're going to add this percent and that percent and that percent together. So that is 13.5% plus 34% plus 34%, which is equal to 81.5%. That is according to the empirical rule. And the last question is to determine the actual percentage of patients that have serum HDL between 34 and 69.1%. So that will involve using the raw data that I have here. So we want to determine how many observations are between 34 and 69.1%. So to calculate the number of observations between 34 and 69.1, we are going to use the function sum product. To use the function sum product, you're going to type in sum product, and then you're going to open parentheses again. So you will have two parentheses here. Highlight your range that you want to find the information from, and then we want that to be greater than or equal to 34. You close the parentheses and then times, open a new parentheses, and then the same range of data. We want it to be less than, to calculate all of the values that are less than or equal to 69.1. Close the parentheses twice and then click enter. So we will have 45 observations between those two numbers. Now, to compute the percentage of our data or that are between 34 and 69.1% precisely, you're going to find the probability or the relative frequency for that, which is the frequency of the numbers between those two numbers divided by the total numbers we have. And remember, from the beginning of the example, we said we have 54 observations. So that means we're going just to say that is equal to 45 divided by 54, and we're going to turn this into a percent. So 83% of our data are between 34 and 69.1%. I hope the demonstration of the empirical rule was clear here. And we're going to move on to the next concept, which is the Chebyshevs inequality to describe any set of data. We're not going to focus on the Chebyshevs inequality since we're not going to be using it for many applications here, except for just to know it. So what Chebyshevs inequality states is that for any dataset or distribution, at least 1 minus 1 over k squared times 100% of the observations lie within k standard deviations of the mean, where k is any number greater than 1. That is at least 1 minus 1 over k times 100% of the data lie between mu minus k sigma and mu plus k sigma, where k is greater than 1. We can also use Chebyshevs inequality based on a sample data. Replace mu with x bar and replace sigma with s. And here's an example to illustrate how to use Chebyshevs inequality or theorem. Using the data from the previous example, use Chebyshevs theorem to determine the percentage of patients that have serum HDL within 3 standard deviations of the mean. So instead of using the previous shape right here and saying, well, I'm going to count 3 standard deviations from the mean here, 3 standard deviations of the mean here, and add all of these percentages. Instead of memorizing all of these percentages, we go ahead and use Chebyshevs inequality to estimate that. So we're going to replace k with the standard deviation, which is in this case 3 standard deviations. So you will have 1 minus 1 over 3 squared times 100%. That will give us 88.9%. And from the empirical rule, we know that is not very close. Actually, it is 99.7%. So this is a good estimate, I would say. The next step is we're going to determine the actual percentage of patients that have serum HDL between 34 and 80.8 within 3 standard deviations of the mean. So that is finding how many observations between those two numbers, and that is 52 divided by 54. That is approximately 96%. So that is the end of the measures of dispersion. And if you have any questions, please come to my class prepared with questions and I will be happy to answer them. I hope this helped you. If there's any part of the video that is not clear to you, please come prepared with questions. Thank you for watching and I will see you in class.